Big data is everywhere. In global industries like healthcare and pharmaceuticals, data science is providing the answers to some of the toughest biological problems. Bioinformatics is a type of data science at the heart of this evolution. Never heard of it? You're not alone. In fact, bioinformaticians are in short supply.
So I think it's very clear that we're in this digital revolution and we have a massive skill shortage. And let's face it, the digital revolution isn't going away. It's only going to get more, so we're going to need more and more people.
ARU is offering a degree apprenticeship in data science specifically for the bioinformatics profession.
Bioinformatics, you can really simply say it's digital biology. It's doing biology on a computer, whereas instead of you might go in a lab and get some test tubes and some Bunsen burners and that kind of stuff, bioinformaticians generally will work on a computer.
So really we can't access biology anymore without technology, and bioinformatics is the discipline that is evolving and emerging to address that need and that requirement. It's at the fundament, if you like, of really understanding biology in the next 10, 15, 20 years.
Our apprenticeship is designed in collaboration with world-leading scientific organisations, all of whom need bioinformaticians.
We use bioinformaticians in all of our research. In the cancer programme, we may be looking just for one spelling mistake in the DNA of those patients that can then be tracked back to the cause of that cancer.
Where our vision is taking us is to think beyond rare undiagnosed disease and think where else does bioinformatics take us in improving healthcare. So this is all now lining up to making the UK the premier place in the world to do precision medicine.
So this is pretty groundbreaking stuff. Why haven't many people heard about bioinformatics and the positive impact data science can have on the world?
It certainly hasn't been around for that long. When I was doing my degree, there was anything such as bioinformatics. It's evolving and there are many, many more people taking an interest in bioinformatics, where you can really bring in the expertise from biology and data analysis together and actually making sense of big data sets.
Bioinformatics is a relatively new field and there is a critical skills shortage. Luckily, there are governing bodies to help people get qualified for the roles.
So the government are investing in training the next generation of bioinformaticians so that the UK will benefit from better health, but we'll also be able to build better businesses on the back of these skills as well.
It's a niche skill set in a new and complex field, but this degree apprenticeship won't limit the scope of your career.
Within bioinformatics, there's multiple different themes. You can be a bioinformatician caring about human health, but you can equally be looking at plant science, or you can be like a friend of mine and do marine bioinformatics.
Skills in bioinformatics are relevant to many sectors. Also now working within some of the big data companies where wearable technologies and home genetic testing are becoming more routine, and so all of these sectors are crying out for new skilled bioinformaticians.
Being able to do an apprenticeship in such a broad, exciting and potentially world-changing subject can propel you straight to the top.
So I left school at 15, then I wanted to apply for an apprenticeship. I think fundamentally being an apprentice and having that maker mindset equipped me to be an entrepreneur more than anything else. That's why I'd recommend that path to any young person thinking about where to go next with their career.
The degree apprenticeship is going to help me stand out because not only do I have a degree level, I will also have those years experience in a business applying that learning which a lot of other courses won't allow you to have on your CVs.
So I would absolutely say go for it because you can't lose. It's a fantastic opportunity to do a degree while working, and the benefits of education and working at the same time are very powerful.
And Anglo Ruskin is the place to do it, ensuring what you learn is super relevant to the experts you'll be working alongside.
Anglo Ruskin University has consulted with a number of employers, big names in the business during the time that the course was actually taking shape, and that's given us the vital kind of intelligence.
I'm always talking to people in bioinformatics and they've heard of our ARU and they've been involved in the process. So I think what ARU have done is really reached out and got the best of the bioinformatics community to really input into this space, and I think that's been a key thing.
So, what does a day in the life as a bioinformatician in training look like?
Day to day, there will be no day that's the same. You'll be in seminars, in lab meetings, you'll be brainstorming, chalkboard talks.
I was worried when I first started my apprenticeship degree that I would struggle to balance all of the work life, study life and personal life, but actually it has been very reasonable, doing 20% of my work time dedicated to the course.
It's not just sitting in a dark room in a cave or tapping on a computer. There's actually quite a lot of personal interaction, and we eat a lot of cake as well.
Sound like something you could get into? Here's what you need.
You don't necessarily need to have great mathematical skills in order to be a great coder. Often bioinformatics is viewed as gluing together various pieces of code. For people who are skilled in coding and coming through into their A-level and bringing on those skills, they can be really valuable.
My degree apprenticeship has given me access to education that I wouldn't have otherwise been able to get hold of. My parents were quite shocked when I took on a degree apprenticeship. My oldest brother was very academic, but I never seemed to be the academic type. But this apprenticeship degree has given me the opportunity to access that academic side whilst also being out in the world of work.
We're looking for curiosity, and we're looking for an interest in computers, but also an interest in how you could apply that knowledge to answer some of the biggest questions that we have left to answer.
And there's never been a more exciting time to forge a career in data science.
Science always needs young, new, bright minds applied to these big problems that can only be tackled when we come together.
I really love studying a degree apprenticeship because I'm able to study something that I'm really engaged in whilst also practicing it and getting paid to do it. So it's just, brilliant. The advice I'd say to anyone who's looking to apply for a degree apprenticeship is be optimistic, think openly, because actually, although you may think you can't handle it, you'd be surprised what's possible.
Once we have the corpus in place, we can start doing so-called named entity recognition. For that, we use the Tagger software that was developed in my group. It does flexible matching of a biomedical dictionary against the text, thereby marking up many different types of biomedical entities. The ones that are of interest to string is species name recognition, which allows us to identify the relevant string species for which to look for gene and protein names. And then we look for gene and protein names. For this, we make use of synonyms to get good recall, that is, identify many matches, and to also get good precision, we use a regular expression to identify certain patterns of bad names, a block list of known bad names, and these bad names were originally found by manual curation. The reason why this is bad news is that that's a lot of work, so we've now changed to a different approach. What we're using is 3 different named entity recognition tools that identify multiple different entity types. This allowed us to define a high-quality consensus, then mask these names, and fine-tune a transformer, that is a language model, to predict the entity type based on textual context. This allows us to predict good and bad matches by looking only at the context, not the names, and then using a scoring scheme to identify which are the bad names, that is, names that typically appear in a context that doesn't suggest that it is the entity type that our dictionary says. With named entity recognition done, we can turn our attention to interactions, and I'll start with physical interactions. For this, we build upon named entity recognition and use a large language model for finding explicit statements in text, such as this one that says that 2 proteins or complexes bind or physically interact with each other. For this purpose, we mask the entity names and use a Roberta model that has been fine-tuned for the task using the complex tome corpus. If you want to learn more about large language models and fine-tuning of them, I've already covered that topic in a separate presentation. This model gives us a score per statement, and we can then calibrate that on the complex portal dataset, which is a database of protein complexes, to obtain posterior probabilities for the individual statements. We then take the best, strongest scoring statement within each article and further aggregate those over all the documents in the corpus to obtain our final confidence score of physical interaction from text mining. In string version 12.5, we will further have regulatory interactions thanks to a new fine-tuned model created on the regular tome corpus. If you want to learn more about that corpus and the complex tome corpus, watch my earlier video on the Jensen Lab corpora. This gives us a directed string network that further, in addition to having direction, has sign on the interaction, so we know which are positive and negative regulatory interactions, and will have regulatory interactions both at the level of expression and post-translational regulation. This will give us the most comprehensive regulatory network and will also help keep string the best network database in the world. Speaking of being comprehensive, we also have functional associations text mined from the literature using a co-mentioning pipeline. This pipeline counts up how many times any two proteins are mentioned together in the literature, counting both at the level of documents, paragraphs, and sentences. We combine this into a single weighted count that puts more weight on the stronger evidence being in the same sentence versus the weaker evidence being in just the same document. We do frequency normalization of these weighted counts to correct for the literature biases that we know are there. For example, P53 will be mentioned a lot more than a poorly studied protein. This approach is remarkably powerful because it's able to extract all relationship types, not just physical or regulatory interactions. On top of that, the statistical nature of the approach gives you a literature consensus. So for something to be strong, it has to be mentioned many times. The downside is that it is unspecified type. We know that two things are mentioned together a lot, so they probably do something together, but we don't know what. For this reason, we also include the large language model results. That is, we take physical interactions and regulatory interactions and we consider them part of the functional association network because they are indeed special cases of functional associations.